Hello, this is Big Picture Walks, Stay-at-Home Edition. Times are special, so this episode will be special too. So I'm gonna talk about exponential growth, and I think this is the perfect time to talk about exponential growth these days. There is a nice link between the history of the human civilization, the history of the world economy, and epidemics. It's really all about exponential growth. I'm going to discuss exponential growth and contrast that with something called logistic curves. So this is exponential growth. And okay, I'm not going to teach you how to solve differential equations. It's really not going to be about that. So far, I'm just giving you this standard equation for any variable x that grows exponentially over time. T is time. And the solution to that is very simple. You realize that the growth rate is constant over time, doesn't change at all, and the solution is an exponential growth function. If your growth rate A is positive, then your solution grows exponentially over time without any limit, so it kind of looks like this, right? It grows ever faster, so if you look at this in the relative terms, the growth rate is constant. A nice feature of exponential growth is that you can define doubling times, and doubling times are constant for exponentially growing processes. So if you take a look at this, here you see how to compute the doubling time, and you immediately see that the doubling time d is just an inverse of the growth rate a multiplied by a constant equal to log of 2. So this is the exponential growth process. Everything grows at this steady rate, and so the process is exponential. Now, contrast this to the logistic curve. Okay, the logistic curve follows this differential equation, which has two parameters. A is the pace of growth, and x bar is the satiation level. And so if you see that, you have two processes happening at the same time. First, you have the exponential growth process, which is in the beginning. Like here, you see you have x dot equal ax, but then you multiply it by this, which is a term that declines as x grows. So as you get closer to the satiation level, the growth rate declines, and you see this here. If x is approximately 0, then the growth rate is just a times x bar. And if x is big, then basically it goes down to 0. So again, I'm not telling you how to solve it. It's a Bernoulli equation. It has a standard method of solving, and so you can get the solution, which is like this. And this is called a logistic curve, which looks like this. Okay, it has a upper bound. So as time passes, you converge to the limit, which is given by x bar, and there is an inflection point here in the middle. This inflection point is where growth ceases to be approximately exponential, and instead the process starts slowing down, eventually towards stopping completely. So the growth rate here, you can easily see is, okay, the growth rate is like this. Again, here, so the growth rate is approximately constant, equal to a times x bar if x is small, and then if x is big in the limit as it approaches the limit, then the growth rate basically tends to 0. So the growth rate declines. And you can also compute the doubling times. The doubling times are given by this formula here, which is not particularly beautiful, but it has this nice property that as x is relatively small, approximately equal to 0, you recover the same formula that we had for exponential growth, only that now the growth rate is a times x bar, but otherwise it's exactly the same formula as we had before. And doubling times makes sense only if there is a perspective of doubling. So if you look at this, you see that once you cross x bar over 2, there is no more chance for x to double, so doubling times don't make any sense beyond that point. This formula is not well defined for x greater than x bar over 2. Why am I telling you this? If you think about economic growth of the human civilization of any country you can think of in a long time perspective, typically you would assume or you would infer that the growth rate tends to be roughly constant. And if the growth rate is roughly constant, the solution is roughly exponential. So you can imagine that there is certain time for a given variable to double. And for example, if you think about pre-industrial times, in particular before the year 1500, and you think about the world population, well, it was growing at a roughly constant rate, so you can compute an approximate time for the world population to double, and that was roughly 1,000 years. But next, in the post-industrial and industrial and post-industrial era, not only population growth accelerated, but also so did global GDP, global output. We are accustomed to growth rates of the range around 2-3% per year, which means doubling of world GDP every 20 to 30 years. This is now kind of the standard growth regime that we're used to. If you think about the digital era, if you think about the computers and internet of these days, what you see is that the total volume of data, the total communication of data and data processing power tends to grow exponentially again, doubling every 2 to 3 years. What do we make out of this? Well, clearly, it seems as if growth has always been exponential, but it's just an approximation. And in fact, what we can relatively reasonably say is that our growth processes are more akin to logistic curves rather than purely exponential processes. So there is some natural upper bound for the variables that we are talking about. So for example, if you think about global population, there is a prospective upper bound. We've already passed, the Earth as a whole has already passed the inflection point. The growth rate of the population is now slowing, and according to the United Nations forecasts, we should expect around 11 billion people by the year 2100. But then it's kind of a plateau. Okay, so you see this logistic curve, it goes up, but then it flatlines and doesn't grow further. So this is what is expected for the world population. Now we don't know what would happen for GDP. We have seen roughly exponential growth so far, but maybe there will be a point of inflection after some points. We just don't know that yet, right? But it's possible, and at a lower scale for like single products or certain technologies, we've seen already that this sort of inflection and then growth slowdown has been typically observed for products and product lines and so on. So maybe this will happen to the whole world in terms of GDP as well. We just don't know that. Okay. We know, by the way, that there is something that grows faster, an order of magnitude faster, and that is data information processing and data communication. Now, it's maybe a good occasion to link this to what we are all fearing these days, which is the coronavirus that is hitting the whole world hard. Again, we are wondering what the time paths are going to be for the coronavirus. What we can say for sure is that it has a very steep growth path, so it has a very short doubling time. It's estimated as of today, which is March 18th. It's estimated that the doubling time is around 6 days for the coronavirus. So roughly every 6 days we have twice as many cases, which is a tremendously high growth rate. Again, these are our two options: exponential growth or the logistic curve. And so what would we expect for the global population? We expect it to flatline eventually. For global GDP, well, so far it looked like this. But okay, it always looks like this in the beginning, but then maybe something may happen. We don't know yet, so we can say for sure. Now, if you go towards the current epidemic situation, we know for sure that there is an upper bound for the number of cases, and that's 7.7 billion people, because that's how many people live on Earth. But of course, we would like this upper bound to be much, 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 much lower. And how likely it is that the actual line will not be at the whole population, or like some people say 60-70% of the population, but way lower. It depends on our actions. But we can be sure that right now we are really, really low on this line. So the approximation of the growth curve with this growth curve is exact approximation. The deviation is so far really slow, but we have to expect something like this eventually. The question is, however, what the parameters are, and especially what the upper bound is going to be. We've seen something like this already for China, but so far for the world, it looks like this. Let's see what will happen. Fingers crossed. That's it for today. Stay at home, stay healthy, and remember, you already have enough toilet paper and enough rice. Bye.